with our review for Exam 8, Chapter 16. This is the next to the last exam, and the last exam will be during finals week. Exam 9 will be on Chapter 18. But we should have enough time to get that one in, get it reviewed, and be set up for finals week. There won't be a comprehensive final, it'll just be on that last chapter. We got to get this one out of the way first. So let's take a look at some of these sample problems. Let's see, I can only get 2 at a time. Let's do 3. All right, which of the following is the strongest conjugate acid? That's the terminology there is correct, but it could be misleading because we normally think of in our previous discussions, when we talk about strength of, we just outright say an acid is strong or weak. We don't think of it as a conjugate acid is strong or weak. We normally think of the conjugate base of the acid being strong or weak. So in this case, what we want to do is just define which one of these is the strongest acid. And it's a little difficult to, we have to rationalize it actually. So let's put our choices up here and see if we can work through them. Let's see, we've got this one, and we'll name them in just a minute, just sort of as practice, because we've already learned how to name acids, but it might become rusty. Okay, or all the same. Okay, so this one, notice, well, they're all acids because this is an acid, that's an acid, that's an acid. We can see the hydrogen here. But this one you may not recognize this one as an acid because it is the conjugate acid of this base, ammonia, which reacts with water and produces the conjugate acid. Plus the conjugate base. So in this case, this acts as the base, or the proton acceptor, and this acts as acid, the proton donor. That makes this the conjugate acid, and this is the conjugate base. So, which one is actually the strongest acid? Well, let's see. Oh, I was going to name them first. Okay. This one is the hypochlorite ion. Remember, with oxygen, we don't say hydro in the beginning. We just take this anion, which is hypochlorite, and the ite becomes us. So we just say hypochlorous acid. Okay. This one doesn't have an oxygen in it, so we have to start the name with hydro. Cyanide, I becomes ic, hydrocyanic. This one would also start with hydro, no oxygen. Fluoride becomes ic, so this is hydrofluoric. And this one already has a name. It's one of the polyatomics that we learned early on. This one is the ammonium ion. Okay. So that doesn't answer the problem, but I thought it's useful to name our compounds ahead of time, just to kind of refresh our memories. Okay. So we're looking for the strongest acid. How do we determine the strongest acid? Well, if we look at the possible reactions that can occur here, if we're looking at an acid ionization, right, we should get a proton and that ion, right? Of course, recognizing that protons never exist free floating. They're always transferred to something. So it'd be transferred to a water molecule. But for the purposes of discussion, this is acceptable. This one would give us, let's get this out of the way. This one would give us a hydrogen plus a cyanide. This one would give us a hydrogen plus a fluoride ion. And this one would give us a hydrogen plus ammonia. Okay, when we assess the strength of an acid, we're looking at the equilibrium expression for each one. And if we write the K for each one of these, it'll start to get weak and getting fresher. If we write the K for each one of these, then the K for this one is going to be like that over this one. So we don't need to write each one because they're going to be built the same way. But the point is, what you're looking for is which one gives you the largest part up here and the smallest part down here. And the way to do that without actually having the numbers, if we had the values for the Ks, it would be a simple comparison. But we're in a situation where we don't have that. So what we're looking for is which one has the highest affinity for electrons, which one attracts electrons the strongest. Because in order to do that, for instance, when you have this, you want to be able to create a very polar bond. In other words, draw electrons this way in order to release that positive charge, that proton. Okay, so the one that has the strongest electron affinity here, or we call it electronegativity, is fluorine. Right, so this fluorine is going to have a very polar bond, and it's going to make the release of this one much easier. So the K value for this one should be the largest. That's the best rationalization I can make of this information without actually having the numbers. All right. So let's look at, see if this one works better. Yeah, not much. 4. Calculate the hydrogen ion concentration in a solution that has a pH of 8.82. This is a simple calculation. If we know, well, we're looking for this one. If we know the pH is equal to 8.82, and that's equal to Sorensen's formula, minus log of the hydrogen ion concentration. Right? So we've got a formula with one unknown, and we can solve for it. First, we've got to move this negative over here. Then we need to take the anti-log of it. And the anti-log on your calculator is the same as 10 to the minus 8.82. Okay, and that's because that logarithm is base 10. So remember, logarithms are the logarithm of this number is the power of 10 that equals that number. So the power of 10 that equals that number is the answer to the question. And in the interest of time, now we got time. I'll run this through my calculator. I like to do this occasionally because sometimes I find mistakes in my review documents. So 8.82, let me change the sign, and then 10 to the x. All right, and we have 2 decimals. So 2 decimals in the log means that this one has 2 significant figures. So 1.5 times 10 to the minus 9 molar equals the hydrogen ion concentration. And it looks like that's A. All right, need to scroll just a little bit. Pick up number 5 and number 6. Okay. A solution is prepared by dissolving 111.9 grams of hydrogen chloride gas. Remember, that's the way we would name HCl if it's a gas. If it's in aqueous solution, then we call it an acid. But at this point, we're making acid from the gas. So the mass that we're putting in there is 119. Oops. Too many ones. 119.1, is it? No. I had it right the first time. 111.9 grams of HCl gas. Okay. In enough water to make 160 liters of solution. So the volume is 160.0 liters. Okay. And the question is, what's the pH? So what do we need to know to find the pH? We need to know what's the hydrogen ion concentration. Okay. In molarity. And molarity requires that we have moles of solute per liter of solution. Here's the number of liters of solution. Okay. We don't have moles of hydrogen ions yet. But we can get there if we convert this to moles of HCl. We'll do that first. So what's hydrogen is 1.01 grams per mole, and chlorine is 3545. Right? It's on the periodic table. 6, 4, 6, 3, 3646. Okay, so we can find the number of moles of hydrogen chloride that we actually put in solution. 36.46. Okay, so that's 3.0691. I'm going to keep some extra decimals to avoid rounding error. This is the number of moles of hydrogen chloride. So how many moles of hydrogen are in solution? Hydrogen chloride, when it goes into solution, completely dissociates. So it's going to make this and this one direction. That means for every mole of this, you have a mole of that. That means we have 3.0691 moles of hydrogen ions for that many liters. So that will give us the molarity of hydrogen ions. Let's see, 3.0691 divided by 160 is 1.918 times 10 to the minus 2 molarity. And that's in hydrogen ions. Okay, so now we can do the calculation. Right? pH then is equal to negative log of 1.918 times 10 to the minus 2. So let me take the log of that and change the sign. All right. So we've got 4 significant figures here, 4 here. 4 significant figures. So technically speaking, we could have 4 decimal places in our log number. Right? 1.7171 pH. Let's see, do we have one of those up there? Okay, the closest one is D, 1.72. All right, that's number 5. And let's look at 6. A solution has hydroxide concentration of 5 times 10 to the minus 4th molar. The pH of this solution is. All right. We can approach this 2 different ways. We can make it the hard way or the easy way. So if we know that hydroxide ion concentration is equal to 5 times 10 to the minus 4. Right. That's 10 to the minus 4. Then if we know what the pOH is, we can calculate the pH really quickly. Or you can go into the expression of this times this, which is always equal to 1 times 10 to the minus 14. Find out hydrogen ions and then calculate that one. But I'd rather do pOH first, because pH plus pOH equals 14. All right, so what's the negative log of 5 times 10 to the minus 4? Right. Calculator time. 5 exponent negative 4. Did I get that right? Yep. And we're going to take the log and then change the sign. So this one is 2 significant figures. We have 3.30 pOH. So that means pH equals 14 minus 3.30. And that's 14.00, in case you're wondering. All right. Oh, I did something wrong. Hold on a second. 3.3. There we go. So this is 10. Let's see. 10.7. 10.7 pH. There we go. And I left off a 0, didn't I? Yeah. 2 significant figures, 2 decimal places. 10.70 is correct. Yep. That was number 6. Let's see, 7, and we can get 7 and 8 together. As water is heated, its hydrogen ion concentration increases. This means that what? All right, so we know that at 25 degrees C, the hydrogen ion concentration in pure water is equal to 1 times 10 to the minus 7 molar. And they're saying if the temperature increases past this, right, increased temperature, then this hydrogen ion concentration increases. Okay? Now, look at our answers. A, water's still neutral. B, hydrogen ions greater than hydroxyl. C, hydroxyl's greater than the hydrogen ions. D, hydroxyls also increase. And E, A and D are both correct. Okay, here's the way you look at this problem. In pure water, this reaction is going on. You're getting hydroniums, which we're calling hydrogen ions here, right? Same thing. Plus hydroxyls. Okay. If the temperature increases, what's happening? The reaction is shifting to this side, right? Because it's producing more hydrogen ions. That's exactly what that problem says. When you heat water, it makes more of these. Where do they come from? They came from here. So if you get these, you're going to get the same number of these. They're both going to be higher, but they're both going to be equal. Right? So B and C can't be right because that says one of these is higher than the other one. But A says water's still neutral. And what's the definition of neutrality? The definition of neutrality is hydrogen ions concentration equal to hydroxyls. Right? That's a neutral solution. So we've still got that condition. That's true. A is true. How about D? Hydroxyl ions also increase. That's true. A and D are both true. So E is the answer. Now, just as an aside, what does that say about the equilibrium constant, the Kw for water? Well, the Kw would be the hydrogen ion concentration times the hydroxyl ion concentration. And we don't include water because it's pure liquid. And what would that do to the K? Well, if both of those values increase, the K is going to go up. So as you increase the temperature, the Kw also increases. All right, let's see, 8. Identify the Bronsted acids and bases in the following equation. A is a Bronsted acid, B is a Bronsted base. We're shortening it from Bronsted-Lowry or Lowry-Bronsted, but it means the same thing. So let's see. Here's our target, our reaction is HSO3 minus plus CN minus, and that yields HCN plus SO3 2 minus, correct? Yes. Okay. By the definition of Bronsted and Lowry, an acid is a proton donor. Right? Which one donates a proton? This one, because it goes from here to there. It loses a proton. So this is an acid. That makes this the base. Okay. So in terms of conjugates, this one now has received a proton. This one can donate a proton. And this one can accept a proton. So in terms of our answers, This would be A, this would be B, this would be another A, and this would be B. As long as they're in the correct order. Yes, they're in the correct order. So AB, which is, our answer would be B. All right, scroll again. Pick up 9 and 10. Okay. Which of the following is a conjugate acid-base pair? All right, I know I went over this one in the lecture. Let's go over it again. What's required for an acid-base pair? Acid-base pair. Well, you need to have something that's common to both of them. This part is common to both sides. Now, this may include another hydrogen. If it's a diprotic or a triprotic polyprotic acid, it may leave a proton behind. But at least one of them here, in this example, gives us this part is the same on both sides, and we only lose one proton at a time. Okay, so let's look at our choices. HPO4 2- and PO4 3-. How about that one? Yeah, notice we've got this part is the same on both sides, and we're missing one proton from here to here. This is an acid-base pair. If we look at the others, test-taking technique for multiple choice questions. If you don't have any squirrely ones like 2 of the above, A and B, A and D, none of the above, those kind of odd ones that incorporate multiples of the other answers, then once you find the answer, you can stop. So we can stop here because we found our answer. The others, you'll notice, like the second one, HNO3- and H2NO3. Well, in the first place, that's not a valid compound to begin with. You don't have HNO3-. NO3- by itself, right? And then you can have a hydrogen on the front of it. That's okay. But that's not even real compounds. The C, HNH4 and NH4+, you're trying to add a hydrogen, no, that can't be. Right? If you have this one, HNO4 and, excuse me, that in H4, yeah, NH4. And NH4+, this is the acid. So the base would be this one. If you remove that proton, right, it comes off with its positive charge and leaves a negative behind it. So that should be a negative. And that never happens either. All right, we want to go to ridiculous. H2F and HF-. If you try to add a hydrogen to an HF, you're going to have trouble because HF- doesn't exist. Well, not for our purposes, it doesn't. H2CN and CN-, that can't work because CN has lost 2 hydrogens. And you can't do that with an acid-base pair. You have to have 1 hydrogen lost. So the only one that works is this one. That pair is a valid acid-base pair. And about 10, I think that's next. Choose the case that is not a Bronsted conjugate acid-base pair. Okay, so the way that's worded means that we've got to look through here and find the one that's not an acid-base pair. Right? So the first one is HCN and CN minus. Correct? That's true. We got this part the same, and we lost one hydrogen. That's a good one. How about B? HNO3 minus and H2N, sorry, I'm in the wrong one. CH3, NH3 plus. CH3, NH3 plus. And the other one is CH3, NH2. CH3, NH2. Okay. Here's the problem for new chemistry students. The proton or the hydrogen ion can leave the molecule any place it wants to. We typically write mineral acids with the acid proton first, like hydrochloric or hydrofluoric or nitric, that way. But you can have molecules where the hydrogen leaves from some other part of the molecule. All you need is to be sure that to find the pair is that the only thing that changed was the loss of one proton. And it takes its positive charge with it. So if this one is one of our hydrogens, then NH3 becomes NH2, and it lost one proton and took the positive with it. So that was good too. HCO2H, HCO2H, and HCOH, HCOH. Okay, this one should just scream at you. Notice we've got two oxygens here and only one oxygen there. That automatically disqualifies this one because it doesn't have the same core. H3BO3, BO3, and H2BO3 minus, H2BO3 minus. Okay, this is good. This is good. We only lost one hydrogen from here to here. D is, that's a good one. And E should also be because we found the one that wasn't. But we'll do them all just to be thorough. HClO2. Okay. And ClO2 minus. Yep. There you go. So we lost this one proton. It left a negative behind. And it also left this group. So that was good. Okay, so this is the one that's bad here. That's 10. Let's see, scroll again. Yeah, 11, just 11. So we'll put it up here in the middle. Calculate the hydrogen ion concentration in a solution that has a pH of 9.16. Okay, this is like the earlier one we did. If the pH is 9.16, that's equal to the negative log of the hydrogen ion concentration. Okay, we want to know the hydrogen ion concentration. We need to put the negative over here. And then anti-log. So this is base 10. That means this is 10 to the minus 9.16 equals the hydrogen ion concentration. And for practice, 9.16, change the sign and do it. There it is. Okay. 2 decimals, 2 significant figures. 6.9 times 10 to the minus 10 molar. And that's B. All right. Let's see who's next. I'm at 15 and 16. Calculate the pH of an acid solution containing 0.044 molar nitric acid. So our concentration is 0.044 molar HNO3. And we want to know the pH. Okay, for strong acids, we've got one proton here. This thing completely dissociates like that. So for every one of these, you get one of those. So this is the concentration of hydrogen ions in solution. But just as a cautionary note, this concentration, let's write in scientific notation, 4.4 times 10 to the minus 2 molar, right? Okay. What's the concentration of hydrogen ions in pure water? Pure water would be 1 times 10 to the minus 7 molar. Okay. We're in good shape because the difference between this one and this one is 5 orders of magnitude. Right? That would be 10,000 times. No, that's only 4. 100,000. This is 100,000 times more concentrated than that. So the pre-existing hydrogen ion concentration in water before we add this is insignificant. So we can go ahead with just this value right here and ignore that one. So what we need to do is take the negative log of this value. All right. That should be fairly simple. 4.4 with an exponent of -2. And then take the log of that and change the sign. So this is two significant figures, 1.36 pH, which is A. All right, that was 15. I think 16 is next. What is the pH of a 4.9 molar solution of HClO4? pH 4.9 molar HClO4. All right. What acid is this? That's the perchlorate ion. So this is perchloric acid, which is very strong, which means it's going to completely dissociate into that and that. Right. So if you have one of these, you got one of those, that is the concentration of hydrogen ions, which is very high and dangerous. And obviously, it's much bigger than 10 to the minus 7, so we don't have to consider the pre-existing hydrogen ions due to water dissociation. So we just need the negative log of that value. Right? I think the point of this problem is to prove that you can have a negative pH. And what's the log of 4.9? 4.9, take the log, and then change the sign. So we got minus 0.69. Yeah, two significant figures, 2 decimals, that's right. pH. Minus 0.69. That's D. We don't often rarely use negative pHs. So this is an exercise in hypotheticals, but it's nonetheless real. All right. So 16, 17, and 18. Yep. '17. What's the pH of 0.25 molar nitric acid solution? Okay, we have hydrogen ion concentration is equal to 0.25 molar. Correct? If it's a nitric acid, HNO3, it will completely dissociate into these ions. Right, so one of those, that's the concentration of hydrogen ions. So the negative log of that value will be our pH. Oops. Yes, I'm sorry. It asked for pH. That's true. I glanced at the next one and threw me off a second. 0.25, take the log and change the sign. So that's 0.602. 0.6, no, 0.60. 0.60 pH. So that's C, the answer. I'm at 18. 18. A solution has a pH of 3.16. So we know the pH. And the question is, what's the pOH? We just need to remember our formula. pH plus pOH equals 14, which, by the way, is equal to pKW. So we know this one. We just need to subtract it from 14. Okay, 4 1 to the 9 is 8, correct? Yeah. And that's 10.84 pOH. All right. Moving right along. Scroll to the next one. 20 by itself. Which of the following is true for a buffered solution? All right. A buffered solution. What does the buffered solution mean? For in this chapter, right there are a large number of different types of buffering definitions, but here we're talking about acid-base buffering. Okay. So the definition of a buffer in these terms is a solution that changes pH very little upon addition of an acid or base. In other words, it more or less tries to hold its ground. If it's at a pH and you add acid or base to it, it's only going to move very little. It may move so little that you can't measure it, but it does move. It just moves a very little. So which one of these statements is true? Well, A says the solution will not change its pH very much, even if a strong base is added. Right? A, that's a good one. How about B? The solution resists any change in its hydrogen ion concentration. That's another way of putting it. C, any hydrogen ions added will react with a conjugate base of a weak acid already in solution. That is definitely true. If we have a weak acid and it dissociates, into protons and what's left over. This is the weak acid. This is the strong conjugate base. Okay, so if you add protons, where are they going to go? Well, they're going to show up right here, react with this, and shift back that way, which consumes some of those protons. Right? So that's a true statement. How about D? The solution will not change its pH very much, even if a concentrated acid is added. That's true. Now, one thing we didn't talk about, that means E is the correct answer. All of them are true. One thing we didn't hammer too hard was something called buffer capacity. There's a finite amount in any solution. There's a finite amount of this and this in solution. So if we were to add massive amounts of hydrogen ions here, you would eventually reach the point where you consume all of these. And now you got a bunch of these left over, and then the pH would really change. But for our purposes, we're only going to add a little at a time, so we wouldn't get much of a change. As long as we're within buffer capacity, we're fine. All right. That was 20. Let's see, got to scroll. Scroll to 24. All right, a solution has hydroxyl concentration equal to 3 times 10 minus 7 and minus 7 molar. The hydrogen ion concentration in this solution is, all right, so we're looking for hydrogen ion concentration. The temptation would be to convert this to POH, subtract it from 14, and then take the anti-log of that negative value back here. But that's the long way around. Right? If we recognize that this expression is equal to 1 times 10 to the minus 14, we can get the answer directly from that. We just plug the value in here, right? Plug that value in there. That means for this solution of this one, hydrogen ions, we take this and divide it into that. So 1 divided by 3.0 times 10 to the minus 7 is equal to the hydrogen ion concentration. I'm tempted to do that in my head, but yeah, I can do that in my head. If you don't have a calculator, you can subdivide this into 2 groups. Right? What's the power of 10? Well, if the power of 10 is in a quotient relationship, it's this one minus that one. 14 minus 7. Actually, minus a minus 7, so it's 14 minus 14 plus 7, which means the power of 10 is going to be 10 to the minus 7. What's this one? 1/3 is 0.33. Yeah, just 33. 2 significant figures. Then we convert it back to scientific notation, move it 1 to the right. That makes this one more negative. 3.3 times 10 to the minus 8 molar is the hydrogen ion concentration. That one up there? Yeah, D. D's the answer. Now you can do that in your calculator. I'm just doing it for fun. See if I can still do things like that without a calculator. All right, that was 24. Let's see, 27 and 28. Okay, a weak acid, HOCl, There's our hypochlorous acid again. HOCl. And if we're going to name it an acid, technically, we got to put it in water, don't we? Is in solution with dissolved sodium hypochlorite. So this is in solution, and this is in solution together. All right. If HCl is added, which ion will react with the extra hydrogen ions from the HCl to keep the pH from changing? Okay. This is a definition of a buffer. The buffer has to have the weak acid and its conjugate base in the proper proportion. And the ideal proportion, I think I mentioned this in the lecture, the ideal proportion is to have equal concentrations of the weak acid and its conjugate base. Exactly equal. That's the perfect place for the pH to be stable. So this one is acid. And it's going to be in equilibrium with that one. So do we have both of those in solution? Yeah, we got this one and we got this one, which produces that one, plus sodium ions. And the sodium ions are spectators. So yeah, we do have this one and we have that one. So now the question, go back to the question, if we add hydrochloric acid, what are we actually adding? Well, we're adding hydrogen ions and chloride ions, right? So sodium and chlorine, that's table salt, right? But they're both spectators because this is a strong acid. It produces that, right? Goes into the reaction here and it's consumed by reacting with the hypochlorite ion. So D is the answer. All right, 28. Which statement is true for a strong base solution with a concentration greater than 1 molar? Okay, strong base. That's my generic base with a concentration of 1 molar. If it's a strong base, it's going to produce this plus that. And the concentration here is going to be 1 molar. All right, that's what we know from what we're given. Now, what are the questions? pH is greater than POH. POH is greater than pH. All right. So what would the POH be? I mean, that seems to be the type of questions they're asking us. What would the POH be? POH would be the negative log of 1 molar. Right? So 10 to what? 10 to what power equals -1? Let's see. The log of 1. All right. Change the sign. Yeah. Okay. So the POH is minus 1.04. What's the pH? The pH is equal to 14 minus a minus 1.04. Right? So that's 15.04. Right? This is a plus. So that's the pH. This is the POH. Notice that E is 2 of these are true. Right? So when you see one like that, you got to look at each one of them to be sure that you don't have 2 that are true. And you can find one that's true, but you got to keep going until you prove to yourself that there's only one that's true. Then that's the answer. Okay, so pH is greater than POH. pH is greater than POH. A. That's true. POH is greater than pH. Well, it can't be both ways. It's either one or the other, right? So B is false. How about C? pH is less than 14. Nope. It's greater than 14. And D, pH is less than 0. No, pH is greater than 0. POH is less than 0, right? If it had said POH is less than 0, that would also be true, and then E would be the answer. But it's not, because the only one that's true in this selection is A. Right? So the key to answering this question is not just the information that's given in the first statement, but what are the answers available? And the answers that are available can inform how you approach the solution to the problem. All right, 28. Let's see, we've got to scroll again. 30. A solution with a pH of 2. Right? We got a solution with a pH of 2. Is how many times more acidic than a solution with a pH of 6? pH of 6. All right, I'm going to go the long way around to prove this one. How many times more acidic? What does that mean? What that means is, say this is solution A, and this is solution B. All right? So the hydrogen ion concentration of solution A is going to be, it's going to be greater than 6, isn't it? Right? Lower pH means more hydrogen ions. So we know it's going to be greater than this one. We just want to know how much greater. Right? So what would be the hydrogen ion concentration here? Well, pH of 2 would equal to negative log of hydrogen ions. Right? So the 10 to the minus 2 molar, right? 10 to the minus 2 would be the concentration of this one, and this one would be 10 to the minus 6. So this one is 10 to the minus 2. This one's 10 to the minus 6 hydrogen ion concentration. How much bigger is this one than that one? Right? Right? Negative 2 is bigger than negative 6. So how many times did we go? Well, what would you have to multiply times this to equal that? Ten to the plus 4, right? Because what is this? Mathematical of powers of 10 minus 6 plus 4 is minus 2. Right? 10 to the minus 2. So 10 to the 4th times bigger. So what's 10 to the 4th? Got 4 zeros. 1, 2, 3, 4. 10,000 times. So the answer is D. This solution is 10,000 times more higher concentration of hydrogen ions, or stronger, more acidic, than is 10 to the minus 6. And the reason for that is this is a logarithmic scale. So for every unit, you change by a factor of 10. Right? So this would be 4 times 2 to 6 is 4 times change. That would be 4 times 10 is, excuse me, it would be 10 to the 4th power. If we add this one, pH 7, that'd be 10 to the 5th power. Or if we went back here to 5, that would be only 10 to the 3rd power. The difference in these two. Okay? That's how we solve this problem. The purpose of that problem is to emphasize the logarithmic nature of pH. All right, let's scroll to our next pair, 32. A buffered solution contains HNO2. HNO2. Right? What is the name of that acid? This is nitrite, correct? There's oxygen here, so we don't say hydro. Nitrite, ite becomes us. This is nitrous acid. Okay. What is it going to do in solution? And how do we make a buffer out of it? If the reaction in aqueous solution is going to be this, yielding that plus this, we need some of this. We need some of that and some of this in order to make a buffer solution. So how do you get it in there? Well, you need some sort of a soluble salt. You need a cation with this one, like sodium or potassium or even lithium, which would be more expensive, but it will still work. So are any of those up there? Yeah, KNO2. KNO2 will give you this species in solution with that one. And that is how we get our buffer. (33). All right, consider the reaction. Acetic acid, C2H3O2, with what? Water, okay, water. And it produces H3O plus. Actually, this ought to be both directions because that's a weak acid. Plus C2H3O2 minus in aqueous solution. This is aqueous. Okay. Which species is the conjugate acid? Well, this is the acid, right? So it can't be this one. This is the conjugate base. That makes this the base, and this is the conjugate acid. Okay. That's why B is the answer. When you put oil and vinegar on your salad and you scarf it down like I did last night, you are consuming everything in that reaction is going into your system. Acetic acid is vinegar. Well, 5% acetic acid is vinegar. Okay, 35. Which of the following is not a conjugate acid-base pair? Okay. Oh, we did one of these like, well, these are different examples. Okay, so we'll do these two. So the first one, H2SO4, H2SO4 and SO4 2 minus. Is that a conjugate acid-base pair? I don't think so. It's got this part's the same, but it's missing 2 hydrogens. You can't do that. Not to have a conjugate acid-base pair. What would be the conjugate base of this acid? Right? If we wanted to do it right, it would be this one. Okay. Just lose 1 proton. That would work. But as it is, it's wrong. How about B? Oh, we found the answer. That's the one that's wrong. The rest of them are right. And if you check them out, look at each one and you find that the base is missing 1 proton and the rest of the molecule is the same as what you started with. Right, so this is the only one that's wrong right here. And I didn't see any oddballs in there. Those are all straightforward mineral acids. Now, except for acetic acid, that's organic. But they all have that protons at the beginning, and then the rest of the molecule. Those are well behaved, so to speak. How about 37? All right. Given the following list of Kas, which of the conjugate bases is the strongest? All right, so let's write all these up here. NH4, HCN, HOCl, and HF. And their Kas are 5.6 times 10 to the minus 10, 6.2 times 10 to the minus 10, 2.9, 10 to the minus 8, and 3.5 times 10 to the minus 4. You know, this would have been useful information on that first problem. Because when you have these values, you know exactly which one is the stronger acid, right? This one right here. Out of that group, this is the strongest acid because it has the largest Ka. But this problem, we're not going for that one. We're going for the strongest conjugate base. So the conjugate base, since these are the acids, what's the conjugate base? Right? NH3, Cn minus, OCl minus, and N minus. So which one of those is the strongest base? The strongest base is produced by the weakest acid. So we've got to find the weakest acid here. The smallest number, right? It's not that one. Not that one. Oh, 10 to the minus 10. Which one of these is smaller? This one right here. Right? That's smaller than this one. So this would be the weakest. I mean, that would be the strongest conjugate base of that group. Okay? That's how you do it. $37, $40, and $41. How we're doing? Okay, we're doing okay on time. Solid calcium hydroxide is dissolved in water until the pH of the solution is 10.39. So we got calcium hydroxide. Right? Notice calcium is always 2+, hydroxide is a -1. So that's how you write it. 2 hydroxyls for each calcium. And this one is going into solution, correct? Yeah, into solution. Until the pH is 10.39. pH equals 10.39. Okay? The hydroxide ion concentration of the solution is what? Well, we don't even need to know that anymore. I mean, it's what I call blue smoke. It's more information than you need. We just need to know what's the pH, and the question is, what's the hydroxyl ion concentration? Well, we know that the pOH is equal to 14 minus 10.39. Right? Okay. So I'm going to use my calculator because I'm going to need that number later anyway. So let's say 14 minus 10.39 is 3.61. That's pOH. So the OH concentration is equal to 10 to the minus 3.61. And let me change the sign here and 10 to the X. There we go. So that concentration is 2 significant figures. 2.5 times 10 to the minus 4 molar. That would be B. Okay. And 41. Choose the pair of concentrations that cannot be in a given aqueous solution at 25 degrees. That cannot be in a given aqueous solution at 25 degrees. Okay. The point of this question has to do with the amphoteric nature of water. How it goes from, I'm going to simplify it like this, like that. So in water at 25 degrees, this one is going to be 10 to the minus 7th molar. This is going to be 10 to the minus 7th molar. And this reaction is always happening in water. So in pure water, that's what you get. But if we write it this way, in terms of its equilibrium expression, then whatever this value is times that value has to be equal to 1 times 10 to the minus 14. Right? So that means if this increases, that has to get smaller. So let's see. The first one is 10 to the minus 13. If hydrogen ions are 10 to the minus 13, what does this one have to be? 10 to the minus 1. Correct? Add these two together, you should get minus 14. Right? So how about A? No. OH cannot be 1 molar. It has to be 1/10 of a molar. So A is wrong. Oh, okay. So we found our answer. And E says all of these can exist. No, we found, all you have to do is find one wrong one to negate E. E can't be. So we found our answer A. The rest of them should be right. Right? What's B? Well, B would be 10 to the first power. And OH would be 10 to the minus 15. Yeah, that gives you 10 to the minus 14. So B is good. How about C? 10 to the minus 3 and 10 to the minus 11. Yep, that gives you 14. C is good. How about D? 10 to the minus 17. We did that one already. So D is good. Okay, so we found our answer. A is the one that cannot exist in water at 25 degrees. All right, that was 41. Let's scroll to 42. Okay. What's the pH of a solution prepared by dissolving 96.1 grams of sodium hydroxide? So the mass equals 96.1 grams of sodium hydroxide in enough water to make 3.2 liters. So the volume equals 3.2 liters. Okay, we did one like this before with a different compound. So this needs to be converted to moles because what's this one going to do? It's going to completely dissociate into those. So if we find the moles of this, we know the moles of that. 96.1 grams. We need to convert to moles. Right? What's sodium? 23? Yeah, sodium's 23. Oxygen 16. And hydrogen is 1.01. 1, 0, let's see, 7, 10, 40, 40.01. Okay, so we'll divide that into 96.1. And we get 2.402. 2.402 moles of hydroxyl. That's not concentration. That's just moles of hydroxide. Okay, so now we can calculate concentration. And what are we going for? We're going for pH. All right, so POH, actually OH concentration is 2.402 moles per 3.2 liters. 0.751 molar. Okay, so let's take the POH that one. If we're going for pH, let's just do POH, negative log of 0.751. And let's see, take the log, change the sign. I get 0.125 POH. So pH is equal to 14 minus 0.125. Let's see, we got we're limited to 2 decimal places. So as soon as I get this, I'll have to round it. All right, I got 13.88 pH. There it is, B. B is our answer. It took several steps, but we knew we were going to end up here. So we needed to know pH. And in order to get pH, we had to know OH. In order to OH, we needed the moles of hydroxide, of sodium hydroxide. So that's the thought pattern. Solve that problem. All right, that was 42. Let's see. Oh, that's it.